All right, welcome to Pod4 Journal Club. Today, we are going to unpack a really fascinating survey paper that finally brings some order to one of the biggest and, let's be honest, one of the most confusing ideas in all of AI, the world model. So let's just dive right in.
It all really comes down to this one question. When you see an AI generate a video, or when a robot is figuring out its next move, what does it actually understand about how things work, about cause and effect? The answer, or at least the beginning of it, is something called a world model. But here's the problem. Everybody in AI uses that term, and almost nobody means the exact same thing.
I love that the paper's authors kick things off with this quote from Einstein. It just perfectly captures the scale of the ambition here. For thousands of years, we humans have been building mental models to try and make sense of reality. And now, we're trying to get machines to do the very same thing, to build their own internal, working models of our world. Okay, so here's our game plan for breaking this all down. First, we'll get into why the term world model is such a mess. Then, we'll look at the paper's amazing solution, a brand new map for the field. We'll walk through 3 levels of AI smarts, from a simple predictor to a self-improving evolver, and see how they operate in 4 different worlds. And finally, we'll tie it all together to look at what this means for the future of AI.
So let's start with the problem itself. Think about it. You've got a team working on robotics. To them, a world model is all about physics, right? Not bumping into things. Then over here, you have a team building a video generator. Their world model is just trying to make sure the pixels look right from one frame to the next. They're using the same 2 words, but they're solving completely different puzzles. It's created a total mess.
So to get everyone on the same page, the paper gives us this clean, foundational definition. At its heart, a world model is just the AI's internal rulebook for how the world works. It's trying to learn cause and effect. You give it a situation, you give it an action, and its job is to predict what's going to happen next. Sounds simple, right? Well, as we're about to see, the devil is in the details.
And here's why this confusion actually matters. If we don't have a shared language, how can we possibly measure progress? How do we know if a breakthrough in making cool-looking videos is actually getting us any closer to a robot that understands that a cup, when dropped, will fall? The short answer is, we can't. And that is exactly the problem this paper sets out to fix. And that brings us to the core contribution of this paper, which is just brilliant. To fix this mess, the authors reviewed and synthesized over 400 different papers to create one single, unified map for the whole field. They call it the Levels by Laws framework, and it's a completely new way to think about what these models can do. What's so cool here is that you can really see the shift in thinking. The old way was just to group models by their job title. This one's for robotics, this one's for gaming. This paper says forget that. The new way is to group them by what they can fundamentally understand. This gets us out of these little silos and creates a real ladder of sophistication.
Now, there are 2 sides to this new map. The first is how smart the model is. The second axis, which you can see right here, is all about what kind of world it operates in. The paper breaks it down into 4 flavors, each with its own rulebook: the physical world of physics and objects, the digital world of code and networks, the social world of human behavior, and the scientific world of abstract ideas.
All right, let's dig into that first axis, those 3 levels of capability. You can really think of this as a ladder, showing a clear path from pretty simple models to something way, way more powerful. So here they are. Level 1 is the predictor. This is basically autocomplete for reality. It just predicts the very next thing, the next word to next frame. Then you climb up to level 2, the simulator. This is where it gets interesting. It can chain those predictions together to imagine a whole sequence of events, kind of like a chess computer thinking 5 moves ahead. But then there's the giant leap to level 3, the evolver. This is like an AI scientist. When its prediction is wrong, it doesn't just guess again. It stops and says, my theory of the world must be flawed, and it actually rewrites its own rules. And this really is the most important idea to grasp. That jump from an L2 simulator to an L3 evolver is everything. The world model stops being just a static tool the AI uses. It becomes what the paper calls a curious living component. I love that phrase. That's constantly testing its own knowledge and running little experiments to get smarter. So now let's bring those 2 ideas together, the 3 levels of capability and the 4 different worlds they operate in. Because this is where the theory gets real, and we start to see the unique and often kind of funny ways that these models fail. This diagram from the paper lays it all out beautifully. You can see how each world has different properties. The physical world, for example, has very strict, formal rules, gravity. But it can be hard to see everything.
That leads to problems like the sim-to-real gap. Then you look at the social world. The rules are way fuzzier. They're just social norms. And models there tend to fail by forgetting who they are, which the paper calls role drift. Each little box is its own unique puzzle.
But what's really fascinating is that some problems seem to pop up everywhere. Compounding error is a huge one. A tiny little mistake in the first prediction snowballs over time until the whole simulation is just nonsense. And then there's that surrogate to reality gap, where a model that's an A+ student in a clean simulation completely flunks out in the real, messy world. These are massive challenges.
And let's put a hard number on just how big those challenges are. The paper brings up a benchmark test that's designed to see if today's best video models have a toddler-level grasp of physics. Like, do they understand that objects don't just vanish into thin air? So what was the success rate for our state-of-the-art models? A jaw-droppingly low 0.262.
What that number screams is that there is a giant difference between making something that looks real and a model that actually understands what's real. Our current models are amazing at creating visually plausible scenes, but they are still complete beginners when it comes to being physically faithful. They can paint a gorgeous picture of a cup falling, but they have no idea that it can't just pass straight through the table.
So why does all this matter? Well, this framework isn't just a neat way to organize research papers, it's a roadmap for what's next. It points directly at the Holy Grail, building agentic AI. And by that, we mean AIs that don't just create stuff, but can actually take action and accomplish goals out in the world. And for these future AIs, the goalposts are moving. It's not enough anymore for a world model to just imagine a future that looks plausible. That imagined future has to be decision-usable. In other words, it has to be so reliable, so grounded in reality, that an AI can confidently base its next action on it. And that brings us to the most powerful takeaway from this entire paper. The path to truly intelligent, agentic AI isn't just about building bigger and bigger L1 predictors. It's about building models that deeply internalize the rules of the world, and crucially are smart enough to update those rules themselves whenever they discover they're wrong. And that leaves us with a pretty wild, thought-provoking question to end on. The journey this paper maps out is a journey from AI as a simple tool to AI as a dynamic, self-correcting learner. So the ultimate question is, what happens when we finally build an AI that doesn't just understand our world, but can actively and autonomously change its own mind about how it works?